Okay, so the definition of electric field is a vector quantity, and it relates the force exerted on a test charge to the size of the test charge. And we can use this information to calculate the electric field. So we can use this equation. E is equal to the force on the charge divided by the charge. So this is the force on the charge. Q prime stands for the charge. And E is not energy, it stands for electric field. So electric field, the units are newtons over coulombs. So you can just write that as N over C. So whenever you calculate the electric field, that's going to be the unit that you're going to have after whatever number value you get. So an important thing to also remember to know about electric fields is that the direction of the electric field is the direction of the force on the positive test charge. So if it asks you to find the magnitude of the direction, it's going to be the same as the direction of the force. Now I'm going to solve a problem for you in your book. This is example problem number 1, and it's on page 483. Okay, so the problem says an electric field is to be measured using a positive test charge of 4 times 10 to the negative 5th coulombs. This test charge experiences a force of 0.6 newtons acting at an angle of 10 degrees. What is the magnitude and direction of the electric field at the location of the test charge? So first off, you need to draw a picture, which I've been forgetting to tell you to do in your homework, so you need to start drawing pictures again. My bad. Not going to mark you down, but you need to do it now. Now I will mark you down. So here's our little test charge. So from this assignment on, draw pictures. And the force, this arrow represents the force, it's at an angle of 10 degrees. So we were given that charge is positive 4 times 10 to the negative 5th coulombs. And the force is equal to 0.6 newtons, and the direction of the angle is 10 degrees above the x-axis. So it's asking us to find the electric field. And because we know the direction of the electric field is the same as the direction of the force, we need to find the electric field at 10 degrees. So we know the direction of the electric field already. So to solve, you can use the equation that we just discussed above. So the electric field is equal to the force on the charge divided by the charge. We can go ahead and plug in our numbers. 4 times 10 to the negative 5th coulombs. Sorry, that should be on the bottom. Our force is 0.6 newtons. So divided by our charge, 4 times 10 to the negative 5th coulombs. And that gives you, when you plug it into your calculator, 1.5 times 10 to the 4th, 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 1.5 newtons per coulombs. That is our value for our electric field. Are there any questions solving this problem? We could give you the charge and the electric field and ask you to find force, or give you the force and electric field and ask you to find the charge. Just basic, simple algebra rearranging the equation. Okay, so next topic is electric field lines. And like they discussed in the video, these are not real. The lines are not real. The electric field is very real. Yes? It's the direction of the force, or the direction of the electric field. What do you mean by it doesn't? In that problem, it didn't, because it gave you already what the direction of the force was, but like we did in our notes last time, when you're given a positive and a negative test charge, we can use the arrows to see we can calculate which way the direction is. So we found that one of the forces was pointing up and one was to the right. There's a problem that we did when we found the angle. We did the tangent of the angle and found that it was equal to 42 degrees. So you can calculate the angle of the direction of the force, and when you find that, that's the same as the direction of the electric field. So in that problem, it already told us the direction of the force. Okay, so electric field lines, they're not real. They are a means of providing us a model of the electric field. So we can get a better idea by drawing a picture. So you remember that video from last Friday with the manic professor and his assistant when she touched the Van der Graaf generator, her hair kind of stuck up. Those could be like electric field lines. The lines aren't real, but it was showing the direction of the electric field. So I'm going to draw some pictures of how you draw the lines of an electric field. So first off, the strength of the electric field is indicated by the spacing of the lines that you draw. So the field is the strongest when the lines are close together, and it's weakest when the lines are further apart. So if like on the state test or on a test that we gave you, we drew the electric field lines, you could figure out where the electric field, where it was strongest by looking at where the lines were closest together and when they spread out and were further apart. So you can kind of get a good idea before you actually solve the problem where that force is going to be. So our first picture, I'm going to draw a positive test charge. And on this one, the electric field lines are drawn perpendicularly away from the charge. So if you have a positive charge, the lines are being directed away. You can also have a negative charge. When you have a negative charge, the lines are drawn perpendicularly towards the charge. So last period I gave an example, way to remember this. So like girls in high school, they like to run to the bad guys. They like to date the bad guys. A negative charge, so they go towards the negative charge, and then they go away from the good guys. So negative, towards, positive, away. Sorry, good guys, they'll come back to you later in life. Yeah, keep up the faith. So you can also do a mixture of charges. So I can have two negative charges and one positive charge. So we're going to use the same rules as we did in example A and B. So for the negative charge, the lines are drawn towards it. This is also in your book. On page 485. And for the positive test charge, they're drawn away. So here's a mixture of away and towards. So there's a few applications of an electric field that we can talk about, and the first is going to be electric potential difference. And this is defined as the work done moving a test charge in an electric field divided by the magnitude of the test charge. So it's the work done in an electric field divided by the magnitude of the test charge. So here's an equation that you can use to find electric potential difference. It's delta V. I don't know why they chose V. Just stands for electric potential difference. Is equal to the work on the test charge divided by the charge. So the units, we're having a new unit now. I'm sure you've all heard of it before. It's volt. This is going to play a role when we learn about circuits and resistance on Friday and Ohm's law next week. So a volt is just joules for work over coulombs, which is the unit for charge. So you can either write joules over coulombs, or you can write V, which just stands for volt. So I'll draw you a picture of what this looks like. So we can have two charges here, two negative charges. I'm going to have a little test charge right here. Positive test charge. That arrow represents the force on the test charge. And I'm going to move it a distance away from the negative charges. And what's going to happen is when you move it apart, it's going to increase the potential difference. Delta V. And the opposite is true when you move it towards. So again, I have two negative charges, then I have my little test charge, positive test charge up here, and I'm going to move it a certain distance towards the negative charges, and this one is going to decrease the potential difference. Which is just delta V. So I will do an example problem from your book on one of these. This one is on page 491. This is example 2, page 491. So this problem reads that two parallel plates are given opposite charges. A voltmeter measures the electric potential difference to be 60 volts, and the plates are 3 centimeters apart. What is the magnitude of the electric field between them? But before I start this problem, I forgot to mention something. We have a uniform field in this problem, and with electric potential difference, you can sometimes have uniform fields. So, sorry, just add a note. Uniform field. So in a uniform field, you have two plates with equal amount of charges, so they cancel each other out. So the field is uniform in the middle, and you can place a test charge in there. And when you can have a uniform field, then you can use the equation that the electric potential is just equal to the electric field times the distance that you're moving the particle. So this equation you're going to be using for almost at least half of your homework problems today. And any problem that you're given on the state test is going to be a uniform electric field. So you can use delta V is equal to electric field times distance to solve those problems. And you can also solve for work by just doing the charge times the potential difference. So those are two important equations when you have a uniform field, when it's labeled a uniform field, that they will give you that you can use to solve the problem. So uniform field is just when you have a plate of a positive charge and a plate of a negative charge that are parallel to each other and they have the same amount of charge of positive and negative that cancel each other out and make it uniform. So this example problem is a uniform field, and they gave you a picture in your book. We'll just draw their picture. So on the top, in this one, they have negative, 4 negatives, and 4 positives on the bottom plate. So we know electric fields flow from away from positive and towards negative. So this is our electric field inside the two plates, and this is our distance separating the plates. So we were given the potential difference is 60 volts, and the distance we can convert to meters. 0.03 meters, and we need to find the electric field. It's a uniform field, so we can use this equation. So to solve, we'll just rearrange the equation to solve for electric field. So electric field is just equal to the potential difference divided by the distance. So that's 60 volts divided by 0.030 meters. And that gives you 2 times 10 to the third newtons per coulombs. So when you're finding electric field between two parallel plates, it's not usually going to ask you the direction that the electric field flows. So you don't need to worry about direction. But do know that it always flows away from positive and towards negative. So you could flip this problem if you wanted the negative plates to be on the bottom and the positive on the top. The electric field would just be the other way. It would point down instead of up. Okay, then our last topic is capacitance. So a few units ago we were talking about gravitational potential energy. So when you lift a book, so I have a book here, and I lift it up, well you can't really tell in the video, but I raise it up and it's increasing its gravitational potential energy, and this can be interpreted as storing energy in a gravitational field. And similarly, you can store energy in an electric field, which is where capacitance comes into play. So capacitance, it's the ratio of the charge stored the ratio of the charge stored to the electric potential difference. So the equation that you use for capacitance, they were smart on this one, C is equal to the charge divided by the potential difference. So a lot of these equations interact with each other. When you know a few variables, you can solve for different things. This big C is capacitance. And we have a new unit. It's named after Michael Faraday. So we know charge is coulombs. Potential difference is volts. So this is just C over V, which is also called a farad. Not a ferret, but a farad. Named after Michael Faraday. So you can write farad, or you can write C over V, coulombs over volts, when you're calculating capacitance. And so an application of capacitance is called a capacitor. It's a device designed to have a specific capacitance. And all capacitors are made up of two conductors, and they're separated by an insulator. And we use these in electrical circuits to store charge. So there's a lot of useful everyday applications for them. So this is all you need to know to complete your homework.